Hello and welcome back. Today's goal of this lecture. Today I will see what is the differentiation in higher dimension. In my complex analysis lecture, I have seen when f is defined from complex to complex is a complex differentiable at a point z0 belongs to C if there exists a prime z0 in the complex number and there exists a function phi which is defined from complex number to complex number with the condition fz equal to fz0 plus f prime z0 times z minus z0 plus phi z, where this phi z is actually the linear approximation, the error where this phi z over z minus z0 as z tends to z0, it goes to 0. This is the complex differentiation. Today I will say actually what is differentiation in real, in multivariable, in complex. At first, just see the graph. At first I had read real analysis. Then I had read multivariable calculus. Because multivariable calculus be a vector which here function defined from R to R. But in multivariable function, here function defined Rn to Rm, which I have studied in linear algebra, and the branch of multivariable function is manifolds, functional analysis, complex analysis, both. And actually our discussion about complex analysis, that means this is actually the branch of multivariable function. Complex analysis, this is actually defined on the complex plane, where notice here this is the real axis and this is the imaginary axis, and here complex analysis is always equivalent to R2, mapping from R2 to R2. Complex analysis, all structure is same. Here only this is the real axis and this is the imaginary axis. F from complex to complex is same as the function f from R2 to R2. That means here in complex analysis, differentiability actually same as the differentiability in R2 space. Now I will say what is the differentiability from Rn when function defined from Rn to Rm. Actually this concept in multivariable calculus, the differentiability I had defined briefly. At first, if you don't see my previous video of multivariable calculus, see the playlist. Then you will understand that each part, each topic briefly. As for example, if we consider one mapping f from C to C and the mapping is such type z goes to z square. That means if we consider here the point I, after the mapping, after the function f would be -1, z goes to z square means x plus iy goes to x plus iy whole square. That means this would be x square plus 2yxy minus y square. And when function defined from R2 to R2, then xy goes to x square minus y square 2xy. This is actually similar. I hope my all viewers have understood this example. Okay. First I will see when function defined from real line to real line. We all of us know when function f is defined from real line to real line, then f is differentiable at the point x equal to a means there exists a well-defined tangent line at a point A. This is actually the meaning of differentiability. That means function is differentiable at a point A means limit x goes to a fx minus tangent line at a point A divided by mod x minus a equal to 0. This is actually the linear approximation around the point A. And f, who is defined from real line to real line, is called differentiable at a point A belongs to R if there exists a number b and there exists a function gamma who is defined from real line to real line with the condition f of a plus a is equal to f of a plus b plus gamma a dot a, where for all a belongs to R with the condition gamma a tends to 0 when a tends to 0. Here gamma a means actually the f of a plus a minus f of a approximately equal to BS, and this is the linear approximation. Consider this as L of S, L of A, X, and since this is approximately equivalent to B of S, that means there exists an error. F of A plus A minus F of A, consider this is equal to B of A is plus gamma A is dot A, where this gamma is the error. Where for all A belongs to A, gamma A when A tends to 0, this goes to 0, then this is actually the best linear approximation around the point A. That means f, when defined from real line to real line, is differentiable at a point A means f is continuous at a point A and f is approximately equivalent to linear approximation. Approximation means f of a plus a is minus f of a is approximately equivalent to b of a. Next I will discuss differentiation from R2 to R2, and I will recommend you please see this part with attention because our main discussion about complex analysis, f from R2 to R2, this is actually same as f from complex number to complex number. So all property actually same. So pay attention in this topic, in this part. fxy differentiable at a point AB if limit xy goes to AB fxy minus tangent plane at the point AB, and since here from R2 to R2, that means here the difference norm of xy minus AB, and at here the differentiation at the point AB, so limit xy goes to AB, this value is equal to 0. We all of us know the equation of the tangent plane at the point A, B, f of AB is z equal to f of AB plus x minus a f of x AB plus y minus b f of y AB. We all of us know this is the equation of the tangent plane at the point AB, f of AB. That means here the tangent plane at the point AB means just put the value. Means a function fxy is differentiable at a point AB if for all points near AB fxy equal to f of AB plus f of x AB times x minus a plus f of y AB times y minus b plus rxy. And obviously this is the tangent equation of tangent plane, where this error term means these rxy. Since f is differentiable at the point AB, that means limit xy goes to AB, rxy divided by square root of x minus a whole square plus y minus b whole square equal to 0. And these rxy goes to 0 more quickly when the denominator approaches to 0 quickly. And the function approaches to the tangent plane is called actually the linear approximation. That means what is the linear approximation? Difference between fxy and tangent plane. This is actually the linear approximation. Difference between the function and the tangent plane. Because when these rxy tends to 0, then this approximation would be the best approximation. And difference between the function and tangent plane is actually the linear approximation. Now we will see the linear approximation in half dimension. When Rn to Rn, then in R, A is mapped to BS. This is the linear approximation in R I have seen. And instead of A is mapped to BS, this is the linear approximation is denoted as L, who is mapped from Rn to Rn. Such type of linear map is actually could be the matrix. That means when function defined from Rm to Rn, when function defined from Rm to Rn, then function is differentiable at the point A belongs to Rm means there exists a matrix A, and this matrix defined from Rm to Rn. That means the matrix A is M cross N matrix. Then f is differentiable at a point A means f of A plus A is minus f of A is approximately equivalent to A is. Where error term EA is equal to f of A plus A is minus f of A minus A is, which belongs to Rn. And as A is goes to 0, EA is goes to 0 because EA is be the error term. That means limit A is goes to 0, EA is equal to 0 is in Rn. And since this is the Rn, that means limit A is goes to 0, norm of EA is divided by norm A is equal to 0. That means if f is differentiable at a point A means there exists a matrix A who is defined from Rm to Rn such that limit A tends to 0, f of A plus A is minus f of A minus A is this norm divided by norm A is, because EA is means this norm of EA is divided by A is, just put the value. This is the norm of EA is, this is the norm EA is equal to 0. I hope my all viewers have understood. And this matrix is called actually the Jacobian matrix. Consider JF since differentiable at the point A. So Jacobian matrix at the point A times A is, this Jacobian matrix is actually total derivative of f at A. This type of differentiation is actually called total differentiation. When function defined from Rm to Rn, this type of differentiation actually called total differentiation at a point A, and the derivative is called as total derivative. When n and m equal to 1, then the Jacobian matrix at the point A is actually the A prime A. And if we want to evaluate Jacobian matrix at the point A times A is vector, this would be A prime A times A. As for example, I will consider R2 to R2 because actually my goal is I will see what is the differentiability in complex analysis. I will see all relation between all calculus. But our goal actually the compare all thing about in complex analysis. So I will see one example which is defined from R2 to R2. Consider one function A which is defined from R2 to R2. And the function is such type f of x1 comma x2 equal to x2 x1. Notice x1 map to x2, x2 map to x1. We have to prove f is differentiable at the point 0, 0. For this, f of 0, 0 comma plus h1 h2 equal to, since x1 map to x2, x2 map to x1, this map would be h2 h1. And this is, we can write f of 0, 0 plus here h1 h2, then the Jacobian matrix would be 0 1 1 0. And here the error term would be 0. We don't need the error term because this function is actually equal to this function. So this is differentiable. This function be differentiable at the point 0, 0, and the total derivative is 0 1 1 0. I hope my all viewers have understood. Okay. Total derivative is denoted as Jacobian matrix at the point 0. This type of example actually very important to understand all differentiability. Next, I will say what is the relation between totally differentiation and partial derivative. F which is defined from U to Rm, where U be the subset of Rn and fx is f1x up to fmx. Then f is totally differentiable at the point A. Here obviously A means vector. Belongs to U means since f is totally differentiable at the point A, that means obviously f is continuous at this point, and whole partial derivative means del f del xi at the point exists where for all I belongs to 1 to n. That means del f del xi, and del f del xi at the point A means obviously since here f is f1 to fm component, that means del f1 del xi at the point A up to del fm del xi at the point A exists. And we all of us know what is the Jacobian matrix. If f be totally differentiable, then the value of the derivative at this point is actually the Jacobian matrix, and the Jacobian matrix at the point A is equal to del f del x1 at the point A. Obviously here f means m components, del f del x2 at the point A, since here f means m component, so this column contain m component. Del f del xm, del f del xn at the point A, this column also contain m components. This is the Jacobian matrix, and this is the relation between totally differentiation and partial derivative. I hope my all viewers have understood this is okay. And if all partial derivative exists, that means del f del xi at the point exists, and this is true for all I belongs to 1 to up to n, and here a be the vector which is belongs to the open interval u, and if this partial derivative is continuous for all I belongs to 1 to n, then f is the totally differentiable. That means this is another condition. If all partial derivative exist component wise and each component of the partial derivative be continuous, then we can tell the function is totally differentiable. Let's see one example. Defined one function f from R2 to R3 such that f of x1 comma x2 equal to x1 whole square plus x2 whole square, x1 cube, x2. Notice here all partial derivative del f del x1 is all the partial derivative. At first notice the partial derivative del f del x1 means 2x1, second component would be 3x1 whole square, then this third component would be 0, and del f del x2 equal to, notice here 2x2, second component would be 0 and third component would be 1, and notice del f del x1 and del f del x2 both are continuous function. So obviously f is totally differentiable because all partial derivative exist and these partial derivative are also continuous at this point. And total derivative would be Jacobian matrix F at the point A vector. This would be 2x1, first component would be 2x1, 3x1 whole square 0, second column would be 2x2, 0, 1, and at the vector at the point A means here A1, A2, A3. Just calculate. Complex analysis, I had read. Complex differentiable means when f defined from complex number to complex number, f is complex differentiable at a point z0 belongs to C if there exists f prime z0 belongs to C and a function phi which is defined from C to C with the condition fz equal to fz naught plus f prime z naught times z minus z0 plus phi z, where obviously since this phi z is adult term, that means phi z over z minus z0 as z tends to z0, this is goes to 0. There exists a nice theorem. F which is defined from complex number to complex number is complex differentiable at a point z0 where z0 is x0 plus I y0 which belongs to complex number. That implies f which is defined from R2 to R2 because complex differentiable means this is equivalent to the function which is defined from R2 to R2 is totally differentiable at a point x0 y0 belongs to R, and the Jacobian matrix at the point x0 y0 has of the form A minus B B A. This is the Jacobian matrix at the point x0 y0. Here the form of the Jacobian matrix is such type because if we multiply two vector w dot z, where w equal to a plus ib and z equal to x plus iy, this is equal to ax minus by plus I times bx plus ay. And we can write this is as a matrix form a minus b ba, and here the vector xy, and this is equal to actually ax minus by and bx plus ay. So in complex differentiation, since this is equivalent to the function which is defined from R2 to R2, this is equivalent to the Jacobian matrix at the point x0 y0, because here the function is totally differentiable at the point x0 y0 I have considered. So Jacobian matrix of the form a minus b ba, and this is has come from this idea. I hope my all viewers have understood this is okay. Jacobian matrix a b minus b means, we all of us know Jacobian matrix means this is actually the partial derivative, and also we all of us know complex differentiable means this is always satisfy the CR equation, and from this Jacobian matrix we can tell del u del x equal to, notice here a, by this we can tell del u del x equal to del v del y, and del u del y equal to minus del v del x. By this Jacobian matrix we can tell, because Jacobian matrix means this is actually constructed by partial derivative. So by this Jacobian matrix we can tell del u del x equal to del v del y, and del u del y equal to minus del v del x, and this is actually the CR equation. And we all of us know when function be complex differentiable, then always be satisfy the CR equation. I hope all viewers have understood what is the complex differentiation, what is the total derivative, all hard dimensional differentiation, all combination have understood clearly. Okay. Today I will stop here. In my next video I will discuss the complex integration. Okay. See you soon. Stay safe and stay positive always. Thank you so much and have a nice day.